Hello and welcome back to our data structures and algorithm series. In this video, we are going to learn about the linked list data structure. The linked list data structure, just like an array, is a collection of elements, just like this image that we see here of a train. So the linked list has, just like the train has a locomotive or the engine, it has what we call the head. Then it's made up of nodes, and the nodes have some data that they carry and also have a link. And the last node does not have a link, but is actually the end, and it's called the tail. So we are going to see this as we move on. So the linked list is number 2 in terms of popularity and usage. So after arrays, the linked list is the most used data structure. It is a linear data structure, meaning that elements in the linked list can be accessed, is actually accessed sequentially from one element to the next, and so on and so forth. As I've already said, just like a train, we have a series of connected nodes that are linked together and also hold data. Then these particular nodes, unlike an array, are stored at different locations in memory. So they're not contiguous. Remember, when you're talking about an array, we say that an array, each element of an array is stored at contiguous memory locations, which means that in the memory, they are stored next to each other. But for linked lists, which is the main advantage of linked lists over arrays, elements are actually stored randomly in memory. That's why we call this a dynamic data structure. Each node, what we call an element in an array, we call a node in a linked list, has two parts. The first part is the data part, and the second part is the address part. So the data part stores the data that you want. It can store any type of data. Then the address part stores the link or the reference to the next node. So the address is also called the link or the next variable, which is a pointer. So you know that a pointer is a variable that stores the address of another object or variable for that matter. Now it's not really the first node, but we normally have a variable which is called the head, which is a pointer that stores the address of the first node. So that particular pointer that stores the address of the first node is what we call the head. And we also have the tail, which is the last node. The unique thing about the tail is that it will always have the null value on its address part. So on its address part, it will always have null, meaning that that is the end of the list. So that is what that really depicts. So if you can just see this animation, so this is how a linked list looks like. So these are nodes, and the nodes have two parts. You can see the yellow part has stored some data, for example, A, and the light green part there is the address part, which points to the next node, which stores B, then points to the next node, which stores C, then points to the next node, which stores D. Then D does not point to any other node, so that is the end of this particular linked list. So this start is what we are calling the head. Then for this node, which is the last node, it will have the value null inside here, the value null. So let's move on and see where, just as a reminder, the linked list falls under non-primitive data structures, meaning they are user defined. It is a linear data structure, meaning that you access elements sequentially from one element to another, and it's dynamic. So arrays, we say it are static because you cannot you cannot increase the size of an array on runtime. But for linked lists, as you are going to see, you can be able to create nodes even at runtime, and they're just going to be allocated different memory locations as you go on. So just remember that a linked list is an unprimitive type, it's linear and it's dynamic. So let's look at the properties of linked lists, some of which we've already discussed. So as I said, each what we call an element in an array is called a node in a linked list. A node has two parts. The data part, like here the data, is storing the value A, and the memory address. Here the memory address is storing the memory address 1013, which is the memory address of a cell in memory for the next node. So if we this particular node is stored at a cell in memory whose address is 1008. So in order to be able now to make a linked list, we must have a head. So the head will store, it's a variable that will store this memory address for the first node, which is 1008. Now these will be able to point to the next node, which has been stored at 1013 and has stored a value B, and the memory address for the next node, which is 1025. The next node has stored a C, and the memory address of the next node, which is 1044. The node at 1044 has a D, and for the memory address part, it has a null. So null means that this memory address, this particular address, is storing a value that is not meaningful. So that is what null means in programming. So this in linked list indicates that this is the end of that particular linked list. And for the end node, we normally call it the tail of the linked list. So this is the tail of the linked list. There's always confusion about the head. So I just want to clarify that the head is not a node in the linked list. It's just a pointer to the first node in the linked list. So always remember that. So let's go ahead and see how the linked list is stored in memory. As I mentioned, in memory, in the memory cell, the linked lists are going to, the nodes are going to be allocated different memory spaces at different locations. So that's why we call it a dynamic data structure. So remember, for each cell, it's going to store a value, which is the data that it's storing, and the memory address for the next node. For the last node, it's simply going to be a null. Again, you remember that when we were looking at an array, they were contiguous. The elements were stored at consecutive memory addresses. But here, that's not the case. So this is how the linked list is stored on memory. So why are linked lists important? So they are very efficient in insertion and deletion compared to the array. You remember, for arrays, because they are stored in contiguous memory locations, and we cannot have an empty between two elements. So if we have an insertion or a deletion, we have to shift items, and that becomes a very expensive operation. But with a linked list, if we want to insert another item, for example here, if we want to insert another item, for example here, we are simply going to point, we're simply going to change this next to point, the next for B here to point here, and then this one is going to point, this one is going to point here, like that. So we do not need to shift D, we do not need to shift A, we do not need to shift anything. We simply change the next link for the previous and the after nodes only. Not actually the after. We only change the next for this particular node, the before, the previous node, and the one that we are inserting. We also point it now to C. So that is how the insertion is done, which is a bit efficient compared to arrays. Linked lists are also efficient when it comes to the usage of memory, because unlike arrays, where if we need to add an item, then more space is going to be created, sometimes even more than what we need. With linked lists, we only create a node when it's needed. So we cannot have empty spaces at any given time, because every node must contain some data. So this then utilizes memory in a better way, because we cannot have memory that is just sitting there and it's not being used. So again, we've said that it has a dynamic size, meaning that we can be able to grow the size of the linked list even on runtime. Linked lists are also used for implementing other data structures. Like the next data structures we're going to look at are the queues and the stacks, and we're going to use linked list to implement them. So they are also important because of that. So let's now jump into the types of linked lists. The very first one is what we've been looking at. It's called the singly linked list. So a singly linked list has nodes that are pointing to the next node, just like what you're seeing in this particular visualization. And the very last node will always point to a null. So this is an example of a singly linked list. A singly linked list is important, and it's actually used in several real-world applications. For example, when you have items in a playlist, in whichever application you're using to listen to music, so normally they are organized in a singly linked list, so that after you listen to music A, it moves on to music B, then music C, then music D, depending on how you've ordered it. So that's just one of the applications of singly linked list. Then you have the circular linked list. So with the circular linked list, at the very end, as you're going to see, instead of having the tail pointing to a null value, we make the tail to point to the very first element, so that now we have a circle. Just like if you choose to loop your playlist. So if you choose to loop your playlist, then you're actually using a circular linked list. Other applications for circular linked list, for example, if I do Alt Tab on Windows, you see, I can be able to move from all the windows that have opened. You see, I can be able to move from window to window and come back to, when I get to the end, I come back to the beginning. So that is another good example of a circular linked list application in the real world. Okay, and then we have a doubly linked list. The unique thing about a doubly linked list is that we have two address paths. So the first address path normally points to the previous node address, then the other one points to the next, just like we've been seeing. So the very first node will have the previous address node pointing to a null, because there's nothing before it. but the ones that are in between normally will have an address of the previous node. So you can see that this 1008 is actually the address of this node A here. So if I go on, you can see that this node is actually also pointing to the previous node as well as pointing to the next node. So this is what we call a doubly linked list. So a doubly linked list is important in scenarios where you need to both traverse the list forward and backwards. And one of the real world applications of this that I'm sure you've used is actually in the browser's history. When you're pressing backwards to go to the previous page and pressing the forward arrow to go to the next page. So they use a doubly linked list to implement that particular feature in web browsers. So that is one of the applications of doubly linked lists. We also have a circular doubly linked list. And as you might have guessed, with a circular doubly linked list, we, instead of having a null here, we have this one pointing. So this one will point to this node like that. And instead of having a null here, then this one will also point to this. So this is what we call a circular doubly linked list. Okay, so please read more about that. In the meantime, let's try this. Feel free to pause if the timer is going too fast for you. Okay, so let's move on. So these are some of the advantages of linked lists. We've already mentioned them when we were talking about the properties of a linked list. So dynamic size, efficient in terms of memory usage, and it's also used to implement other data structures. On the other hand, for the disadvantages, of course, because we are storing, because we're also storing the memory address for the next node, so we are going to use more memory compared, for example, to an array. So we're going to use more memory compared to an array. So that's a downside to linked lists. Also, you cannot have a random access. Remember, for arrays, we could have a random access to an element by using the index. But with linked lists, you have to traverse. You have to move from one node to the next node until you find the value that you're looking for. So you cannot have random access. For singly linked lists, you cannot traverse backwards. So you can only do this in a doubly linked list. Also, as you're going to see during the practical, it's a bit challenging to implement linked lists and its operations. Okay, so let's give this a try. Okay, so let's move on. Now, all operations that are possible on all the other data structures that we've looked at are also possible with linked lists. And during our practical, we should be looking into implementing these operations. So traversal is simply going through, visiting each node one after another, from the first node all the way to the tail. Insertion is adding a node. You can add a node either at the beginning or at the end or in between the nodes. Deleting can also be done anywhere, either at the head or at the end or in between. And searching is traversing the linked list in order to find a particular value. Updating is when you want to traverse, find a certain value and change that particular value in the node. And these are the time and space complexities for the different operations. So I'm just going to talk about, for example, insertion. So when you're inserting at the head, it's just an O of 1. So this is the best case scenario. When you're inserting at the end or in between, because you have to traverse first before you insert, so you're going to get an O of N for insertion there. That's the same also for deletion. If you're just deleting the first node, O of 1. But if you have to traverse before you delete, then O of N. So these are the applications of linked lists. When you have a scenario where you need to assign memory locations on runtime, then you use the linked list. So for dynamic memory location. For implementing other data structures like the tree, the graph, we're going to see how to do that using linked list. It's also used for implementing the undo and redo functionality in most applications. When you're using the next and the previous buttons in order to move from one image to another or move backward, most of the time you're using a linked list. Also, as we've said, music players use the linked list for managing their playlists. Circular linked lists are also used for round-robin scheduling algorithms, for example, in networking. So round-robin is everyone has a chance, and when we get to the end, the first one, the chance goes to the first one again, like that. So that is what we call round-robin. Then, as we've said, for the browser's history, we normally store those particular pages that you visited in a doubly linked list. It's also used for pagination in different applications, so that it can only display a chunk of data until you want to move on to the next page. Then it will be able to enable that. Okay, so let's give this a try. Okay. Okay, so we are at the end of this. We've been able to learn what a linked list is. It's just a collection like the array, only that the items are stored in nodes, and each node has a data value and also an address to the next node. And these nodes are stored randomly at different locations on memory. Also, we've seen that a linked list has operations just like the other data structures, like insertion, creation, deletion, searching, etc., etc. And we've also gone through the time complexities, and particularly we've said that when it comes to insertion and deletion, linked lists are more, they're preferable and offer a better time complexity compared to arrays. So that is the end of this theoretical part of linked lists. Next is the exciting part, which is the implementation in Visual Studio Code using Python of linked list operations. So we're going to begin with the creation and the insertion operation. So see you in the next video. Thank you so much for sticking to the end. Bye bye for now.